Okay, so here we're going to find the electric field, a distance d from the end of a solid cylinder with charge q. Assume it's uniform and it's got some length L and radius r. Now, certainly one way to do this is to break this cylinder up into little tiny disks, find the electric field due to each disk, and then integrate over a bunch of disks. And you might say, well, how do you get the electric field for a disk? Well, you make a ring and you integrate over rings. So that's one technique to do this, and we've done that technique before. Here I want to do it all in one chunk. So what I'm going to do is I'm going to have a little bit of charge. I'm just going to make my normal tiny little box of charge, and I'm going to say that that has some amount of charge dq. Well, what kind of an electric field does this little bit of charge make? It makes the electric field that a point charge makes, because it's a point. There's nothing fancy about it. It's just given by Coulomb's law. It has a little tiny bit of charge dq, so it creates a little tiny field dE. My job is to sum over all those dEs by looking at all the little boxes of charge in this cylinder. Okay? Of course, this is a vector, and in order to add vectors, you have to break into components. And so we'll look at the x component and the y component. Now, one thing to consider is that if I go all the way around, up and down a particular ring, I'm going to have just as many pieces on the bottom as I have on the top. And the pieces on the bottom, they tend to point up and to the right, and the pieces on the top tend to point down and to the right. And so the up-down components are going to cancel. And really the only thing I need to worry about is the x components. So let's see what that looks like. So we'll look at the x component, and this I can just add like numbers. I just integrate it up, and that goes like cosine of theta. You may say, well, what's theta? Well, this is theta, right? And so is this, right? And so now we know that we can find theta by looking at the length of this side divided by the length of this side, okay? And so all I do is I plug in dE, which is just Coulomb's law, but with a tiny bit of charge. And now here's the question. I haven't said what dq is yet. I don't know how to integrate over dq, and so I have to express it in other terms. So dq is charge per unit volume times volume. Why charge per unit volume? I've got a solid object. It's got a volume. If I take all the charge and I break it up into little squares, each charge has a little charge per unit volume times an infinitesimal bit of volume, right? I could choose to make my volume dx, dy, dz. That's a little square. Or, since I have a cylinder, I can choose to express the volume as s, ds, d theta, dz. That's polar coordinates plus a z. So if you've taken Calc 3, this should be pretty familiar. Okay, so now if I make that substitution, okay, so all I've done is I've traded dq for the thing that I wrote above, and I've traded cosine theta for z over r, and this looks pretty messy. It doesn't look pleasant. It doesn't really get much more pleasant. But now at least I can set up the limits and simplify a little bit. So notice that s can go all the way from 0 all the way to the edge. So that's r. Theta, that goes around in this direction. That's just a circle. We're going all the way around 0 to 2 pi. And then z. So z is the distance from the charge. That has a minimum distance of d, because we're a distance d from the edge. And then, of course, if the cylinder has a length L, the maximum distance I could be away is d plus L. So this looks complicated, but I just want to reinforce this idea that I'm taking little boxes of charge. I'm figuring out how far away that box of charge is from the point that I'm looking at. I'm coming up with a formula for R that involves other things, and then I'm letting those other things vary. Z can be longer as I come back here. Z is now a bigger number. I'm letting S become a different number. S is typical variable you would use for cylindrical coordinates. Okay, so this integral, it's really not that bad an integral. You have to do 3 of them, but none of them are that bad. And if you do it, you end up with this, which is indeed the answer that you would get if we attacked the problem the first way, by first making a ring, and then filling in the ring, and then filling in the cylinder by making lots of these disks, one after the other. Okay, hopefully this is more helpful than confusing.